Okay, good morning everybody. Welcome to the second day of the NASA Gregory G. Leptoukh second online Giovanni workshop. This is your host, Jennifer Brennan. I've got 9 a.m. Eastern Standard Time, so I'd like to go ahead and get started. But first I would like to go over a few housekeeping items related to this webinar. First, to ensure best audio experience, the conference has been placed in silent mode. However, if you have any issues or any questions, what you should do is enter them into the Q&A pod, which you'll see on the next screen, located on the lower right-hand corner of your screen. This works like a chat. Second, this webinar will be recorded and posted online to our NASA Earth Data YouTube channel and also linked from the NASA Goddard disk site after the workshop. Speaker presentation files are also available for download at the end of each talk. The program layout is as follows. Each of our speakers' talks is 1 hour long. There are 30 minutes allocated to the presentation with a 15 minutes Q&A period that follows the talk, and then we will follow with a 15-minute break just after the question and answer period. Questions will not be answered using the raising hand function. It has been disabled. And again, we will take all questions using the Q&A pod at the end of each talk. What I'd like to do next is turn it over to our workshop organizer, Dr. James Acker, who is a senior support scientist at the NASA Goddard Earth Sciences Data and Information Services Center, or the GESS DISC. He will go over today's agenda and begin with a few opening remarks. It is my pleasure to introduce our workshop organizer, Dr. James Acker.
We have a oceanic focus, even though the first presentation by Pavel Kishcha is about phenomena in the atmosphere. He will be talking about the meridional distribution of aerosol optical thickness and cloud fraction over the tropical Atlantic Ocean. Following that, we'll hear from Adnan Al-Azri speaking to us from Oman. I'm sorry, Pavel Kishcha is speaking to us from Israel. Adnan Al-Azri is speaking to us from Oman, and he's going to be going over the mesoscale and nutrient conditions associated with the massive 2008 Cotyledonium polycricoides bloom in the Sea of Oman and the Arabian Gulf. And following Adnan, we will hear from John Lerter of the EPA, which is the Environmental Protection Agency in Florida, and he will be doing a talk on the use of satellite remote sensing to improve coastal hypoxia prediction. Hypoxia also is known as dead zones in the offshore area where there is low oxygen conditions. We'll take about a 2-hour lunch break after that, and we will hear from Boomjun Kil. He is, I'm sorry, I forgot his affiliation at this point, but he is affiliated with studying the phenomena in southern Louisiana. He is going to be talking about the advection of a fluvial source into the center of the Gulf of Mexico after Tropical Cyclone Isaac. And I have to take a personal note on this, that it was inspired by something that I put on the web a few months ago. And he and his colleagues and his professors followed up on that, did a great job. So you'll like to hear about that. And finally, we'll be hearing from Joanna Vojnova, who is from the University of Delaware, and she'll be speaking on phenomena in the Delaware Bay, the wind zooplankton, ecosystem-wide influence of seasonal wind-driven upwelling in and around the Delaware Bay. And as we're looking forward to a windy day, as weather conditions change in this area, it may be something that's happening as she speaks. I just want to put out a note today, as this seminar is going on, as the webinar is going on, we'll also be following what's going on with the ESA Comet Landing Mission, which should wrap up just about the time we're done wrapping up with the webinar today. So good luck to our colleagues in the ESA. And now we will hear from Pavel Kishcha, and Jennifer will introduce. Thank you.
Hey, thank you, Jim. It is my pleasure to introduce our first speaker for today, Dr. Pavel Kishcha, who is a research scientist in the Department of Geosciences at Tel Aviv University in Israel. Pavel?
Thank you for the introduction, and hello to everybody. As you can see on the screen, the title of my presentation is Hemispheric Asymmetry in Cloud Fraction and Aerosol Optical Thickness over the Tropical Atlantic. Let us start with with the question what the importance is of studying atmospheric asymmetry in cloud cover and aerosols. In general, why is it important? As known, the two parameters, clouds and aerosols, determine solar energy reaching the Earth's surface. So the presence of hemispheric asymmetry in cloud cover and aerosols could lead to the hemispheric imbalance in solar energy reaching the Earth's surface between the northern and southern hemispheres. And consequently, it could affect climate formation and its changes. So it is really important to study hemispheric asymmetry in cloud cover and aerosols. Previous studies show that over the global ocean, there is pronounced hemispheric aerosol asymmetry and no noticeable asymmetry in cloud cover between the northern and southern hemispheres. The presence of hemispheric symmetry in cloud cover contributes to the balance in solar energy reaching the surface in the two hemispheres. And it was interesting to find out if cloud cover remains symmetrical relative to the equator over the area with strong hemispheric aerosol asymmetry. In the current study, we focused on the tropical Atlantic Ocean because this area is characterized by significant amounts of Saharan dust producing pronounced hemispheric aerosol asymmetry over the tropical Atlantic. And our main point in our study is that over the tropical Atlantic, not only is Saharan dust responsible for the pronounced hemispheric aerosol asymmetry, but it also contributes to significant cloud fraction along the Saharan air layer, also known as SAL. This significant cloud fraction in the area of SAL, together with clouds over the Atlantic intertropical convergent zone, contributes to hemispheric asymmetry in cloud cover over the tropical Atlantic Ocean. The presence of hemispheric asymmetry indicates some physical mechanism responsible for this hemispheric asymmetry. And investigating this mechanism is essential for our understanding of climate and its changes. So our current study is focused on understanding the mechanism responsible for the hemispheric asymmetry in cloud cover of the tropical Atlantic in the presence of pronounced aerosol asymmetry. This slide represents a meridional distribution of 10-year mean MODIS-based cloud fraction and TRIM monthly accumulated rainfall, zonal average over the tropical Atlantic during the 10-year study period from 2002 to 2012. So it is obvious, and we can see this meridional distribution for the winter months, January in the left panel, and for the summer months, July in the right panel. It is obvious that there is no hemispheric asymmetry in the winter months, while in the summer months in July we got an entirely different picture with hemispheric asymmetry in cloud fraction with maximum over the tropical North Atlantic. The cloud fraction averaged separately over the tropical North Atlantic is 20% higher than that over the tropical South Atlantic. You see that in each month, in January and in July, the main maximum in cloud in cloud fraction coincides with the intertropical convergent zone, which is characterized by intensive rainfall. In contrast to January, in July, significant cloud fraction can be seen to the north of the intertropical convergent zone. And this cloud fraction can be as high as 0.8, which is even higher than the average cloud fraction over the whole tropical North Atlantic. And this significant cloud fraction to the north of the tropical Atlantic, together with clouds over the tropical Atlantic, or over the intertropical convergent zone, produced or responsible for the hemispheric asymmetry in cloud fraction, and this could lead to the hemispheric imbalance in solar energy reaching the sea surface over the tropical Atlantic Ocean. To determine causal factors for this phenomenon of significant cloud fraction to the north of the Atlantic intertropical convergent zone, we looked at meridional distribution of 10-year mean MODIS-based cloud fraction, monthly accumulated rainfall, and modeled dust aerosol optical thickness zonal average over the tropical Atlantic in July. We found that the significant cloud fraction to the north of the intertropical convergent zone can be associated with the maximum in dust aerosol optical thickness over the latitudes of South in the North Atlantic between 12 and 24 degrees north. And looking at this picture, a question arises if the presence of Saharan dust is responsible for the significant cloud cover to the north of the intertropical convergent zone, or not. To answer this question, we analyzed possible relationship between modeled dust IoT and cloud fraction in the area of the Saharan narrow layer. And this slide represents spatial distribution of 10-year mean modeled dust IoT and MODIS-based cloud fraction. So it is clearly seen that the ocean area of South with Saharan dust transported across the Atlantic Ocean is covered by significant cloudiness with cloud fraction up to 0.8, 0.9. And this is in addition to the main maximum in cloud fraction, in cloud cover over the Atlantic intertropical convergent zone. There is a strong difference between the two maxima in cloud fraction, the two zones of significant cloud fraction in the tropical North Atlantic. High values of cloud fraction in the intertropical convergent zone is accompanied by intensive rainfall. By contrast, the area with significant cloud fraction along the Saharan narrow layer is characterized by essentially low precipitation. To quantify changes in dust aerosol optical thickness, cloud fraction, and monthly accumulated rainfall with distance from the Sahara, we analyzed these parameters average over 6 zones, each 6 by 6 degrees, located in the intertropical, located in the area of SAL, in accordance with the direction of dust transport. In our analysis, we used level 3 of MODIS cloud fraction data with horizontal resolution 1 by 1 degrees, which was supplied by Giovanni database, so that there were 36 grid points in each zone of 6 by 6 degrees. This provides us with an opportunity to accurately average cloud fraction over the specified zones. What you can see in the right panel is zone-to-zone variations of 10-year mean modeled dust AOT in the top panel and MODIS Bay cloud fraction and trim rainfall in the bottom panel. One can see in the top panel, one can see a sharp decrease of approximately 300% in dust aerosol optical thickness from zone 1 to zone 6. Cloud fraction also declined from zone 1 to zone 4, also less pronounced than dust. A strong decline in dust AOT is because of gravitational settling of dust particles, mainly cost fraction. I would like to draw your attention to the fact that the strong decline in dust AOT from zone 1 to zone 3 was accompanied by no changes in precipitation, as you can see in the bottom panel. When over zone 1, 2, 3, the rainfall, trim, accumulated rainfall was less than 20 millimeters per month. Therefore, the washing out of aerosols by rain does not account for this spatial decrease in dust AOT from zone 1 to zone 3. And this proves that gravitational settling accounts for this sharp decline in dust with distance from the Sahara. Over zone 1 to 3, there is significant cloud fraction of approximately even over 0.8, and in the presence of very limited precipitation, less than 20 millimeters per month. This indicates that clouds in zones 1 to 3 are not developed enough to produce significant precipitation. And this can be explained by the effect of temperature inversion below the Saharan air layer base. To examine temperature inversion over the specified zones, we analyzed vertical profiles of 10-year mean MERA reanalysis atmospheric temperature in July, average over the specified zones. And so it is clearly seen that temperature inversion exists over zone 1, 2, 3, and 4, and temperature inversion disappears over zone 5 and 6. The presence of temperature inversion over zone 1 to 4 led us to the idea of a physical mechanism responsible for cloud cover formation along SAL. The temperature inversion over zone 1 to 4 prevents deep cloud formation on the one hand, and this explains limited precipitation in these zones. On the other hand, meteorological conditions below the inversion include include significant relative humidity and the presence of large amounts of settling dust particles together with marine aerosols. Mineral dust particles are known to be ineffective cloud condensation nuclei, CCN, unless they are covered with soluble materials. And in accordance with Levin et al. Paper in Journal Geophysical Research published in 2005, airplane measurements of dust over the ocean showed that dust particles can be covered by sea salt. So coating of settling dust particles with sea salt could modify them into effective CCN. So if it is the case, the meteorological conditions below the temperature inversion includes a large number of effective CCN, which is suitable conditions for the formation of shallow stratocumulus clouds. To examine properties of clouds in the area of the Saharan air layer and the possible relationship between these properties of clouds in the area of SAL and Saharan dust, we analyzed available data on cloud droplet effective radius over the specified zones. This slide represents histogram of effective radius of cloud droplets for liquid water clouds in the specified zone 1 to 4 along SAL based on MODIS level 3 gridded monthly data with horizontal resolution 1 by 1 degrees in July 2010. The data was supplied by the Giovanni database. It is obvious that cloud droplet effective radius increases with zone 1. This is zone 1, 2, 3, 4. It is obvious that on average effective radius of cloud droplets increases from zone 1 to zone 4. And this can be explained by the decrease in CCN associated with the decreasing number of settling dust particles with distance from the Sahara. And this is in accordance with the aforementioned sharp decline in dust AOT with distance from the Sahara, which you can see in the right panel. So this relationship supports the suggested physical mechanism of cloud formation below the Saharan aerial base. Now again about vertical profiles of atmospheric temperature. There was no temperature inversion over zone 5 and 6. Over these zones, we consider the presence of developed clouds, which are capable of producing strong precipitation. Such developed clouds could explain the observed precipitation up to 110 millimeter per month over zones 5 and 6. Some people could suggest that significant cloud fraction in the area of SAL is due to cloud fraction contamination by heavy dust loading. So it is kind of artifact. And we are going to prove that it is not the case over the tropical Atlantic. Indeed, in heavy dust loading situations such as dust storms over deserts, MODIS may consider the aerosol-laden atmosphere as cloudy. During dust storms over deserts, observed aerosol optical thickness values range from 2 to 5 or even higher. Over the tropical North Atlantic in July, aerosol optical thickness is essentially lower. Strong aerosol optical thickness exceeding 1 is a rare phenomenon. Even 1 is a rare phenomenon. To demonstrate that AOT exceeding 1 is a rare phenomenon over the tropical Atlantic, this slide represents histogram of aerosol optical thickness in July 2010 based on MODIS level 3 daily data with resolution 1 by 1 degrees over the whole tropical Atlantic in the left panel and over the latitudes with SAL from approximately 12 to 24 degrees north. One can see that over both the whole tropical Atlantic and over the latitudes with SAL, AOT hardly exceeded 1. Therefore, the effect of cloud fraction contamination by heavy dust loading cannot contribute significantly to cloud fraction averaging over significant territories in the tropical North Atlantic. Consequently, cloud fraction contamination does not account for the observed 20% hemispheric asymmetry in cloud fraction over the tropical Atlantic in the summer months. And therefore, one can conclude that hemispheric cloud fraction asymmetry is not an artifact, but a real physical phenomenon. So far we discussed hemispheric asymmetry in cloud cover. Now let us move to the hemispheric asymmetry in aerosols, in aerosol optical thickness over the tropical Atlantic. This slide represents a meridional distribution of 10-year mean total aerosol optical thickness zonal average over the tropical Atlantic Ocean in July. We compare here between Miser based aerosol optical thickness and modeled AOT based on NASA GEOS 5 model product, also known as MERA-ERA aerosol reanalysis. The pronounced hemispheric asymmetry in aerosols can be clearly seen over the tropical Atlantic with maximum over the tropical North Atlantic. One can see that modeled AOT shows similarity to Miser aerosol optical thickness data. The modeled data were used in our study in order to estimate the contribution of various aerosol species to hemispheric aerosol asymmetry over the tropical Atlantic. We use the NASA GEOS 5 model coupled with Gokart aerosol module, including five aerosol species such as desert dust, sea salt, sulfates, organic carbon, and black carbon. The GEOS 5 includes all processes which aerosol particles are involved in, such as aerosol production, transport, wet and dry deposition. Meteorological fields from the NASA MERA reanalysis were used as initial and boundary conditions. An important feature of GEOS 5 is including aerosol data assimilation using AOT retrievals from MODIS sensor on board the NASA Terra and Aqua satellites. This data set is called MERA aerosol reanalysis, or just MERA-ERA. To estimate the contribution of various aerosol species to hemispheric aerosol asymmetry, we analyze their meridional distribution, which and you can see this meridional distribution of various aerosol species in July based on 10-year MERA-ERA data. You can see that dust aerosols dominates other aerosol species over the tropical North Atlantic. And of course, dust is the major contributor to hemispheric aerosol asymmetry over the tropical Atlantic. Dust AOT averaged separately over the tropical North Atlantic is 1 order of magnitude higher than that over the tropical South Atlantic. This slide illustrates spatial distribution of dust aerosol optical thickness based on 10-year mirror data in the winter months in January and in the summer months in July. One can see that in contrast to January, in July, Saharan dust can reach Central America and contribute significantly to hemispheric aerosol asymmetry over the tropical Atlantic in the summer months. Our study showed that there are strong seasonal variations of hemispheric aerosol asymmetry over the tropical North Atlantic. The hemispheric aerosol asymmetry is most pronounced during the season from May to July, when large amounts of dust are transported across the Atlantic. And there is no noticeable asymmetry in aerosol optical thickness between the tropical North and South Atlantic Ocean in September-October. To illustrate the contribution on various aerosol species to seasonal variations of hemispheric aerosol asymmetry, here we show medial distribution of these various aerosol species during the season of pronounced hemispheric asymmetry in July, and in the left panel, and during the season with no noticeable asymmetry in aerosols over the tropical Atlantic in October. As mentioned, during the season with pronounced hemispheric aerosol asymmetry, dust is the major contributor to this hemispheric asymmetry. While during the season with no noticeable hemispheric asymmetry in aerosol over the tropical Atlantic, the contribution of carbonaceous aerosol to the total AOT in the tropical South Atlantic is approximately equal to the contribution of dust AOT to the total AOT in the tropical North Atlantic. And this is my last slide, which I'm going to show you what happened with cloud fraction during the season of pronounced aerosol asymmetry in July in the left panel, and during the season with no aerosol asymmetry in October. You see that during the season of pronounced aerosol asymmetry over the tropical Atlantic, there is hemispheric asymmetry in cloud fraction with maximum over the tropical North Atlantic. While during the season with no aerosol asymmetry, there is no noticeable hemispheric asymmetry in cloud fraction. So this is an additional evidence that hemispheric asymmetry in cloud cover can be caused by hemispheric aerosol asymmetry. And conclusions. As mentioned, over the Atlantic Ocean, not only is Saharan dust responsible for the pronounced aerosol asymmetry, but dust also contributes to a significant cloud fraction along the Saharan air layer. The significant cloud fraction in the area of SAL contributes to hemispheric asymmetry in cloud cover over the tropical Atlantic, which could lead to the hemispheric imbalance in solar energy reaching the Earth's surface over the tropical North and South Atlantic. Mirror error showed that over the tropical Atlantic, dust and carbonaceous aerosol were distributed asymmetrically relative to the equator, while other aerosol species such as marine aerosol and sulfates, were distributed more symmetrically. And finally, there are strong seasonal variation in hemispheric aerosol asymmetry. It is most pronounced during the season from May to July, when dust AOT average separately over the tropical North Atlantic is one order of magnitude higher than that average over the tropical South Atlantic. And there is no noticeable aerosol asymmetry in September-October, when the contribution of carbonaceous aerosols to total AOT in the tropical South Atlantic is approximately equal to the contribution of dust to total AOT over the tropical North Atlantic. Thank you for your attention.
Okay, thank you, Pavel. What we'll now do is move to the question and answer period. Questions for our first speaker, please type those into the Q&A pod on the right-hand side of your screen. Also, as you can see below, Dr. Kishcha's PowerPoint presentation is available for download. If you highlight the file, you should be able to see the option for downloading that file. Okay, any questions? Go ahead and type those into the Q&A pod if you would. So the first comment was from Dr. Acker, who said, thank you, he enjoyed the talk, it was very easy to follow. I agree, great job. Any questions? Okay, so the first question, Pavel, is what is driving the OC and BC asymmetry?
The asymmetry in carbonaceous aerosol is caused by the transatlantic transport of the biomass burning aerosols during the season of September-October with no noticeable aerosol asymmetry over the tropical Atlantic. We have maximum in biomass burning smoke over the tropical South Atlantic. And these aerosols is because of biomass burning in Central Africa is a factor which contribute to the high presence of carbonaceous aerosol over the tropical South Atlantic.
Okay, thank you, Dr. Kishcha. And the next question is, have you had the chance to use the seasonal analysis function in Giovanni 4 for this research?
No, we just analyze our data month by month. No, we just data we're downloading from the Giovanni portal, but all other analysis we're conducting using our OS means.
Okay, thank you, Pavel. Any further questions? Don't be shy. Any questions, anybody? Okay, here's a question here. Okay, this question is coming from a participant in the Philippines. He wants to ask about the relationship between aerosol, naturally occurring, and man-made pollution in cities, etc., and do they too contribute in the behavior of our seasonal dynamics in the tropics?
I think that the tropical Atlantic is a unique place where natural aerosols dominate other aerosol species, particularly over the North Tropical Atlantic. So desert dust from the Sahara is the major contributor to hemispheric aerosol asymmetry there. And in our region, we consider that at least over the tropical North Atlantic, dust aerosol dominate all other aerosol species.
Okay.
In other area, it could be some also effect and anthropogenic aerosols, but in general, over the global ocean, the effect of natural aerosols should be stronger than effect of man-made aerosols.
Okay, thank you for your response. The next question is, you presented 6 spatial zones on a single map and then did further analyses on each of these
Hello?
zones. Can you hear me?
Please repeat the question.
Okay, it's a comment and question combined. You presented 6 spatial zones on a single map and then did further analysis on each of these zones. Is this a useful capability for Giovanni to develop?
This was just a useful capability to analyze changes in different parameters with distance from the Sahara. We used Giovanni database and level 3 data with horizontal resolution 1 by 1 degrees. And all other analysis was just to find out some relationship between different parameters we analyzed. So we use Giovanni database only as source of data, not a specific tool for the conducting analysis.
Okay, thank you, Pavel. And just a note to everybody, if you do have a question, feel free to send that so that everybody can see it. It doesn't need to be directed specifically to our speaker unless you prefer that. But if you enter it for everyone to see, all participants will have an opportunity to view the question as well. Okay, so Jim.
I can see another question, please.
Yes, okay. So the next question is, does your research show any connection between Saharan dust and the formation of tropical storms and hurricanes?
It's a difficult question. We showed connection between the Saharan dust and significant cloud cover along the Saharan air layer. And there are some other previous studies show some relationship between dust and tropical cyclones, but it is beyond the scope of our study.
Okay, thank you, Dr. Kishcha. Are there any further questions? I'll give it just another minute or so. If there are no further questions, the next thing that we will do is we will take a 15-minute break. And so, okay, one comment coming. I will stand by for the upcoming comment. Adnan, if you are online, what we will do is double check your audio before you, present for the second talk of this morning, okay? And Dr. Lerder, I will then promote you up to presenter status during the break. Okay, Jim, did you have a comment? Okay. So the comment is, Keith's question was about whether the analysis done for the study would be a useful analysis capability in Giovanni. So I think, Dr. Acker is asking your opinion, Pavel, whether or not you think the type of analysis you conducted would be a useful capability to add to Giovanni.
I think so. All our analysis is based on data provided by Giovanni. So I think it's just a good illustration how Giovanni database can be used for conducting analysis of atmospheric processes, of aerosol, clouds, and their relationship. So I think this, yes, it's just a good illustration of using data from the Giovanni database.
Okay. Thank you, Dr. Kishka. Are there any further questions? I think, Jim, if you want to discuss, further capabilities for development with the Giovanni tool, it might be a good idea for you to discuss offline with Pavel. Okay, let's move next to our 15-minute break. Oh, excuse me. Pardon me, there's one more, and let's just take this final question, and then, you could be in contact with the speaker who could address your questions offline as well. This will be our final question. We will then move to the break. Okay, based on the assumption that aerosol contributes to particulates in the upper atmosphere, do affect the severity of air pollution, which, for example, dust, smoke particles from factories in China. How do these affect the weather in a nutshell? So let's see.
Sorry?
So I think the question is, how do aerosol particulates in the upper atmosphere, affect the severity of air pollution? For example, dust, smoke particles from factories in China. What would you say how these types of contributing factors affect weather in a nutshell? So I'm rewording the comment. Hopefully that makes sense and is in line with what the participant is asking. Does that make sense?
Yes, I think it's a good question. The aerosol, anthropogenic aerosols in China, together with desert dust from the Gobi Desert, could affect aerosol content over the Pacific Ocean, and which also significantly contribute to the hemispheric aerosol asymmetry over the Pacific Ocean. With maximum over the North Pacific Ocean between 40 and 50 degrees north, and over the Atlantic Ocean we have the maximum in aerosol between 10-20 degrees north, and over the Pacific Ocean between 40 and 50 degrees north. And so we have hemispheric aerosol asymmetry, strong hemispheric aerosol asymmetry over the Pacific Ocean, and this is because of anthropogenic and dust aerosol which is transported across China. And these aerosols could also affect cloudiness over the Pacific Ocean. Just further analysis is needed to do that, to get the results.
Okay. Thank you, Dr. Kishka. What we'll do now is move to our break. What I've got here for you is information regarding the poster session URL, should you care to participate on Friday. Just a reminder, on Friday you will not be joining us or me as your host in the online meeting room. You will go to the URL listed below to view the PDFs and address any questions to the speakers individually by way of email. Is that accurate, Jim? That's my understanding of your process for the poster session.
And I would like to thank you, Jennifer, for your support during my presentation, and also for the James, Acker, and you for the opportunity to present our presentation at this Giovanni workshop. Thank you.
Oh, you're quite welcome. My pleasure, sir. Okay, so we will take a few minutes